we're going to go over Unit 3, Worksheet 3, question number 2. The question states, suppose that during volleyball practice, you lost 0.91 kilograms of water due to sweating. If all of this water evaporated, how much energy did the water absorb from your body? Express your answer in kilojoules. So, I like to, start by reading the question, but the next thing I'm going to do is I'm going to go through and see if this is going to be a heating or cooling curve. So that way I know whether I need to draw a heating curve or a cooling curve. So, once again, going back through the question, suppose that during volleyball practice you lost 0.91 kilograms of water due to sweating. Well, in that first sentence, it doesn't necessarily tell me if I'm going to be adding energy or removing energy, if I'm going to be heating up or cooling down. Right now, I can kind of assume that I'll probably be heating up because of sweating, but I don't know yet. I'm going to keep reading through the question and seeing what other information they give me. If all of this water evaporated, oh hey, that's actually a key word. That can really help us figure out what it's going to be. We only see that word evaporation, on our heating curve. So that alone should tell me it's going to be a heating curve. I can keep reading to see if there's anything else that does support that. How much energy did the water absorb from your body? Oh, absorb. That's going to be another keyword that tells us this is going to be a heating curve, E+ on the x-axis and T on our y-axis. So this is going to be a heating curve. Now, evaporated, that means it's going from a liquid to a gas. What that means is our curve should be a flat line in that region as we go from our liquid to our gas. Now, typically on a heating curve for water, when we go from a liquid to gas, that would occur at 100 degrees Celsius, but 100 degrees Celsius is the boiling point of water. Evaporation doesn't necessarily occur at that temperature because, well, it happens on your body, which is not going to be at 100 degrees Celsius. So that's why I'm going to leave the temperature at which evaporation occurs blank. After we have drawn our heating curve, what I like to do is I like to draw a table that corresponds to the table we took notes on that identifies the different information we have in our problem. So I will be looking for our energy, which is Q, our mass, which is M, a change in temperature, that delta T, and then finally we're going to be looking for a change in temperature, telling us heat capacity, a change from a solid to a liquid, which tells us our heat of fusion, or something that goes from a liquid to a gas to liquid for our heat of vaporization. I like to set up my table with those variables on the left, just like we have it set up on our table, and then the information I can fill in on the right. Well, looking through the question, I'm going to see if I can see if there's anything that tells us what the energy. If all this water evaporate, how much energy? So we're going to be trying to find out how much energy we have. Now, energy is typically going to be in joules. Oh, at the end, express your answer in kilojoules. That means once I calculate my joules of energy, I'm going to need to take it to some number of kilojoules. That's going to be the very first item on my table I have here, which is also going to be the very first item in our table when we took notes. Next thing is going to be the mass. Mass is typically in grams, so suppose that in volleyball practice you lost 0.91 kilograms. 0.91 kilograms. Our unit's typically going to be in grams, so we're going to need to go from our answer 0.91 kilograms and get it to grams. Actually, let's do that right now while we're thinking of it. So we can start off with our 0.91 kilograms, put it on the top of our ladder, and we're going to try to get to grams in our ladder at the very end. But we need to figure out how we get there. Well, we're probably going to need to go from some number of kilograms to 1 gram. That will allow us to cancel out those units, kilograms on top, kilograms on bottom. Well, if we have 1 gram of that, we can use our table that we took notes on when we did our foo-foos and ladders, the conversions from one unit to another. And that table tells us when we have 1 gram for our base unit, we have 0.001 kilograms. So at this point, we can multiply everything up across the top, 0.91 times 1, that gives us 0.91 grams on the top, and then everything on the bottom, which we just have that 0.001. And because I crossed off the kilograms, that's not going to show up. Well, I need to now divide the top by the bottom. So 0.91 grams divided by 0.001, that's going to give me 910 grams. So this is going to be our mass in grams. I can put that over my table now. I know that we have 910 grams. Well, now for the change in temperature. Well, I start off at one temperature, it's a flat line, ends up at the same temperature. It's going to just say, hey, our change in temperature doesn't matter. It's not going to affect this problem. So what we're going to do next is see if there's a change in temperature, which tells us our heat capacity, C. Well, there's no change in temperature. It's not going to be our heat capacity. Now, is it going to be our heat of fusion? That's a solid to liquid, liquid to solid, or the key terms melting or freezing. Well, looking through the question, I don't see that information, so I'm going to cross this off. It's not going to be that. Well, that probably means it's going to be heat of fusion, or heat of vaporization. So let's take a look and see if that's what's occurring. Heat of vaporization, we're looking for the keywords vaporize, evaporate, boil, or condense, or anything that goes from a liquid to gas or gas to a liquid. Okay, look. If all of this water evaporated, that's going to be one of those keywords, evaporate. That means we're definitely going to be using our HV. Well, the HV, for this is sweat, which is made out of water. We can use the heat of vaporization for water available at the top of this worksheet, which is going to be 2,260 joules of energy per, they say gram. I like to always rewrite it as per 1 gram. So it takes that much energy to vaporize, go from a liquid to gas, or to condense, go from a gas to a liquid, 1 gram of that substance. Now, we can actually write this two different ways, and I always like to rewrite it just to see which one I want to use. 2260 joules of energy vaporizes, condenses, boils, or evaporates 1 gram of the substance. We can also write that 1 gram of that substance requires this much energy to vaporize, boil, condense, or evaporate. After I've rewritten my fraction both ways, what I like to do is to see what unit I'm solving for. My question mark is going to be for the energy joules. So I'm going to circle the joules in my conversion, my heat of vaporization. Now, because I'm solving for joules of energy, I'm going to use this first conversion factor because it has my joules on top. I'm going to start off my ladder with those joules on top. I'm going to draw my ladder down here on the bottom. Hopefully that's long enough. And then I'm going to fill in the very beginning, my 2260 joules per 1 gram. I'm putting the joules on top because I'll be trying to get my answer in joules. What I'm going to need to do next is to put in the other information I know. Well, hey, my change in temperature, that value right above it, it's crossed off. I'm not going to use that for this problem. I am going to have to use my 910 grams. Because we have grams on the bottom, I'm going to put my grams on the top to cancel out. 910 grams, so that way my units cancel out. At this point, the only unit I have on the top is joules, and I'm out of units on the bottom. At that point, I should be good to multiply across the top, and then multiply across the bottom to solve for my answer. So, up on top, 2,260 times 910. I ended up with, that's a big number, 2,056,600 joules. I'll put my commas in there just to make this a bit easier to read. And then I multiply on the bottom, 1 times 1, no units, that gives me 1. So I can simplify my units, divide by the top, 2,056,600 by the bottom, that 1, and that's going to give me 2,056,600 joules for my answer. That's how much energy is absorbed from your body. Oh, but there's one more thing I need to do with this problem, which is to convert it to kilojoules. Actually, maybe even before I move even further, I should make sure that this answer makes sense. Well, for this problem, it takes 2,260 joules of energy to completely vaporize or evaporate 1 gram of water. Well, I have 910 grams, so it should take me more energy, probably 910 times as much, to vaporize that same amount. So I should end up with a bigger number than 2,260. Well, 2,056,600 is a bigger number than 2,260, so that does make sense. So at least that makes sense. Now I can go from that to my kilojoules. So I'm just going to go over and set up another ladder over here. I'm going to start off with that same value, my 2,056,600 joules of energy. And I'm trying to go from joules to kilojoules. Well, I know that from my table on how to convert with metric units, that when I have 1 joule can be a base unit, I'm going to have 0.001 kilojoules. This will allow me to cancel out my units, joules up on top, joules on the bottom, leaving me with just my kilojoules. Because that's the unit I'm trying to get to, I can now put that second line to say equal to. So now I'm going to multiply across the top that 2,056,600 times 1 kilojoule, 0.001 kilojoule, gives us 2,056.6 kilojoules. And that's going to be over 1, which I think by now we can probably just say simplifies, divide by 1, gives us that answer, 2,056.6 kilojoules. So for this problem, how much energy did the water absorb from your body? So the water absorbed 2,056.6 kilojoules of energy. And this is going to be our answer for Unit 3, Worksheet 3, question number 2.